welcome back, and now we'll have Mark talking about the computer.
Okay, thank you. All right. So over the past few years, I've given a few different sets of lectures aimed at mathematicians, and they've touched on quite different topics, and many of them, maybe a couple of you have seen variations of them before. Ones I'm going to give here are quite different in spirit to ones I've given in the past, partly motivated by Bernd Sternfels, who was the main driving force behind a review article that we wrote last fall in collaboration with Shanak Day, Dmitry Pavlov, and Anastasia Balovich. So I'm going to give the archive number here. And the first maybe 1.5 of my 3 lectures will largely be following the material in that review article, although I hope to go far beyond it by the end of my lectures. But Bernd was very adamant that he wanted to see a step-by-step explanation from the beginning to the end of how it possibly is that the amplituhedron arises in theoretical physics. And we sort of dragged our feet on this for a long while because, you know, to the physicists, many of those steps are completely uninteresting. And so often, you know, in other series of lectures that I've given to mathematicians, we start with what we consider to be the fun stuff. Like, oh, here's the exciting stuff. Clearly, this is what's going to get you all excited, not this other boring stuff. An analogy would be like if you were trying to talk to a physicist, you know, and you were saying, hey, we encountered this cool integral. Okay, let me start by telling you what a measurable set is. Okay, because you need to know that to make sense of this symbol, right? Okay, so that's kind of like a rough analogy of what it feels like for me as a physicist to give maybe the first lecture or so. Like we consider this stuff to be so boring that we never talk about it. But maybe it's good to talk about it. So yeah, that's going to be the motivation. So, but in order to yeah, let me start with the end, because I've been told it's always good to start lectures so that the audience feels comfortable with something. So let's fix integers, positive integers, n, k, and m, such that n is greater than 3 and k plus m is less than or equal to n. And let's fix a totally positive n by k plus m matrix Z. Fortunately, we know what that means from Laura's lectures. Okay, then the tree-level amplituhedron A of Z subscript n k m is defined as the image of the positive Grassmannian, sorry, the totally non-negative Grassmannian grk comma n under the map So when I write this map, I think of C being a k by n matrix that represents, in the manner Laura described, an element of the Grassmannian grk comma n. And when I multiply it on the right by this n by k plus m matrix, the result is a k by K plus M matrix. So I view this as an element of the Grassmannian GRK K plus M. And now I think I can put a period because I think I finished this sentence. Okay, so that's what the amplituhedron is. It sounds deceptively simple. You pick a certain positive matrix and you look at the image of the positive Grassmannian under matrix multiplication by that fixed matrix. Okay. So the goal of my lectures will be to explain how it is that we see this arising in physics. Are there any questions about just this definition? It's going to be a long time till I come back to this. Probably won't be until my third lecture, but it would be irresponsible of me not to get this on the board early on. Yeah.
So I'm always a little like confused by the fix a totally positive matrix.
Yeah, me too.
Is there like a canonical matrix that comes out of the physics eventually?
No, definitely not. In fact, we're particularly interested in studying this thing as a function of Z. Okay. And it's so it's an important question to ask. To what extent, and I'll have to defer this question to the experts, but it's important to ask to what extent the structure of the amplituhedron is independent of the choice of Z. And at least we always have in mind considering Z to be sufficiently generic that it should be independent of the choice. But actually, that question allows me to segue nicely into an important point, which is that there's kind of a difference in philosophy, I think, between some of the math community and some of the physics community. And I think you saw a bit of this in Nima's lectures yesterday, because a lot of mathematicians that we talk to are interested in things like combinatorial and geometric structures, whereas in physics, the things that we encounter are often formulas. So like mathematical expressions, specific rational functions, so there's always, of course, a duality, right? You can think about cohomology classes abstractly, or you can think of cohomology classes as being represented by specific differential forms. And the two different points of view complement each other and are useful for different things. So the physics viewpoint that's going to be permeating my lectures is going to be from the point of view of we're going to look at formulas, see where those formulas come from, and try to understand those formulas geometrically and combinatorially. And so the formulas that we will encounter will be, in the simplest cases, rational functions of the choice of this matrix Z. Okay, and Nima also mentioned this briefly in his one of his later lectures, and I will hear more about it from Simon Tellin later on. The notion of positive geometry is particularly useful because it's a context where the correspondence between a geometry and a form is very sharp, because you can say, in the case of positive geometries, in fact, you can say that there's a unique, we call a canonical form associated to a positive geometry. So rather than having to worry about some very long, complicated rational function, say, as a physicist, we can just declare, oh, it's the unique function corresponding to such and such geometry. So that's the story. That's an example of the kind of story that we like very much when we encounter some complicated calculation in physics, but then we realize, oh, but we can just tell a simple story that encapsulates the why that formula exists and what structures it has. Okay, but now I need to, having given the sort of very highfalutin overview or introduction, let's go back to the very beginning. Okay, so the specific so for the few physicists in the audience, the amplitudes that I'm going to start talking about are those of tree level, color ordered Yang-Mills theory. Okay, so this is actually the quantum field theory that describes the actual interactions between quarks and gluons that make up essentially all of the matter in our universe. So the point is that this theory, this is a theory that describes massless spin-1 particles. Okay, now I'm going to define that phrase. Okay. A massless spin-1 particle is a pair of two elements in complexified Minkowski space. I'm sorry that my epsilons look very similar to the element symbol. That's just the way it is. Okay. So C13, just as an aside here, C13 just denotes four-dimensional complex vector space with the inner product that A dot B is defined as A0 B0 minus A1 B1 minus A2 B2 minus A3 B3. So it's the inner product with signature +1 -1 -1 -1. And in the physics convention, in order to highlight the special role, in order to highlight that we've got a signature +1 -1 -1 -1 metric, we don't label the four components here 1, 2, 3, 4. We label them 0, 1, 2, 3. Okay, so C13 just denotes four-dimensional complex space with that inner product. Okay, I haven't finished a sentence here quite. Subject to P dot P equals 0, P dot epsilon equals 0, epsilon dot epsilon equals 0. Oh, and sorry, and one more, and P not equal to 0. That means not identically equal to 0. Okay, are there any questions about this definition? This is going to be kind of definition 1. Later on in this lecture or in a subsequent lecture, I'm going to give a few other definitions that are kind of equivalent, but have some advantages compared to this one.
Really silly question.
Yeah, please.
So it's a spin-1 particle.
Yeah.
Kind of all your conditions are at 0. Like where is spin-1 encoded in here?
Well, spin-1 is merely the fact that we have an epsilon at all. So, for example, thank you for bringing that up. In most of Nima's lectures yesterday, he was discussing what we call spin-0 or scalar particles, which are characterized entirely by a momentum p. So when he talked about his kinematic space, for example, he was talking about the space of four component vectors, and he didn't have the epsilon at all. And so he wouldn't have the analog. If the particle didn't have spin-1, you wouldn't have the epsilon, you wouldn't have these equations, and you would only have these two conditions. And if you wanted to make it massive instead of massless, you could put a number there instead of 0.
Maybe along those lines, should I have some intuition for what epsilon means?
Oh yeah, thank you. Okay, good. Yeah, so the three spatial, I'll answer first your question by describing P. The three spatial components of P describe the direction in which the particle is traveling in our three spatial dimensions. The 0 component is the energy of the particle, and the epsilon describes the polarization. So particles with spin-1 are, for example, like light, photons that comprise light. So light traveling to us from the sun can be polarized in different directions. That's why, polarized sunglasses can be useful because they can filter out certain polarizations and keep other polarizations. And the polarization is described by this vector epsilon.
Last question, what's the zero component of polarization?
Oh, it doesn't have anything. Okay. There's nothing particularly special about the zero component. Because come back to that question in just a second, because when we do a recharacterization of this into a more convenient choice of variables, I think I'll be able to give a better answer. All right. Any other questions? Okay. For n greater than 2, an n particle amplitude, or how about the n particle amplitude, is a rational function. I'm describing it, but in a second I'll give an actual definition of n particles Okay, so now I'm adding a new subscript that runs from 1 to n to describe the momenta and the polarizations of my n particles, subject to Okay. And this formula, this one did play a key role in Nima's talk yesterday. This is called momentum conservation. Okay, so let me recopy the formulas that I have there. These equations give a first definition of the n particle kinematic space. Okay, so if you just think, we have a collection. So we have some ambient space here that's 8n complex dimensional. Okay, so we have an 8n complex dimensional space. And the n particle kinematic space is a subspace within that that's defined by these equations. What is the dimension of that subspace? Anyone care to guess? Sorry? 4. No, it's certainly more than 4, but there is a -4 because we've got 4 linear equations here. Okay. So here's how to think about it. We have, and let's look at the P's and the epsilons separately. So the P's, each P is a 4-component object, but subject to this condition. So we have 3 n independent choices of Pi. Now let's look at the epsilon. For a given, even back, I could have said this in the case of a single particle. For fixed P, the space of, or the set of epsilons that satisfy these two equations is now 2-dimensional, because epsilon is a 4-component object and has to satisfy these two conditions. So that's 2-dimensional. So we have 2n choices of epsilon I. But then we have these 4 equations that have to be satisfied. So these equations define a 5n-4 dimensional subspace of this kinematic space. Now, in fact, as I'm going to emphasize shortly, the actual kinematic space we're interested in is far smaller than this, because the amplitudes, we're going to construct them in a minute, have a structure that, first of all, makes them independent of some of these variables. And so effectively, the actual space we're interested in is lower, is even smaller. Okay, but that was just a descriptive, that was a description of what amplitudes are. Let me now give an explicit constructive formula. Okay, AN is defined as follows. Okay, first, a Feynman diagram is a connected plane tree graph, in this case, with n external vertices of degree 1 and any number of internal vertices of degree 3 or 4. The external vertices are labeled 1 to n in clockwise order, just by convention. So, for example, here are some examples. Okay. So these are very similar. I mean, these are very similar to Plavet graphs in the sense that I could draw them inside a circle here if I wanted to, and we often do that. But I don't yet have any distinction between white and black vertices. We're going to come to that maybe in the next lecture. But for the moment, I don't have any notion of that. However, I do have the specification that I only allow vertices, internal vertices of degree 3 or 4. Yes.
Why do we restrict ourselves to planar diagrams?
Right. So that's because in the specification of the theory that I had on this board before erasing it, I said that I'm looking at what we call color ordered amplitudes. Okay, so basically in a nutshell, once you've solved all the planar diagrams, they determine all the non-planar ones. Okay, so I've drawn here, these are all three distinct Feynman diagrams relevant for n equals 4. These are the three diagrams for n equals 4. And as an exercise, if you want to, you should try to enumerate for n equals 5 and n equals 6. So for n equals 5, there are 10 diagrams. For n equals 6, there are 38. And you can try to enumerate them. Okay, now we're going to decorate these a little bit more. We're going to give an orientation to each edge. And the internal edges arbitrarily, but the external edges, by convention, outgoing. Okay, so let me add this, say, in purple. So the external edges are those that connect to the outside here. And I choose them to be outgoing. That graph doesn't have any internal edges. These two graphs have internal edges, and it doesn't matter. You can make any choice you want. Next, assign each edge a pair E epsilon. EI epsilon I on external edge I. These are actually the E epsilon of the n particles that we are considering. And I can assign other variables the internal edges. So for example, over here, here I'll call this one, I'm not gonna write them all out because it would take too long. So this edge here will be P1 epsilon 1. This edge will be P2 epsilon 2. But here, let me call this P5 epsilon 5. This edge. Okay. Now, associate to each graph a product of vertex factors. Okay. And the vertex factors look like this. Every time you see a cubic vertex, labeled with labels A, B, and C. This is shorthand. A, B, and C here are integers that I'm using as shorthand for the pair, you know, PA epsilon A, PB epsilon B, PC epsilon C. So every time you see a cubic vertex, you throw in the numerical factor I over root 2 epsilon a dot epsilon b epsilon c dot p a minus p b plus cyclic in a b c. So this thing has a cyclic symmetry under cyclically exchanging labels A, B, and C. Okay, and I didn't quite leave myself enough room, so I'm gonna draw the next one at the top of this board. If you have A, B, C, D, you associate the factor I times epsilon A dot epsilon C, epsilon B dot epsilon D, minus I over 2 epsilon A dot epsilon B, epsilon C dot epsilon D, minus I over 2 epsilon B dot epsilon C, epsilon D dot epsilon A. Okay, and there's one last step with the convention. If any arrow is reversed. Let me explain what that means. And we're going to use some explicit examples in a minute. So you see in this formula and in this formula, I've chosen all my edges to be directed outward. But when I go to actually do this computation, like, if I look at this vertex here, I've got 2 edges outward and 1 edge inward. This is the edge I'm calling number 5. So when I apply these formulas, and I'll do that in a minute, on the right-hand side of these formulas, I won't put actually P5, I'll put minus P5. And I won't put epsilon 5, I'll put the complex conjugate of epsilon 5. Okay, we're going to do some explicit examples in a second. And there's one last step. Sorry, two more steps. Then act on that product of vertex factors with the differential operator This is not the way it's usually phrased in quantum field theory textbooks, but it's kind of easier. Requires less machinery. And finally, sum over all diagrams to obtain AN, the n particle amplitude. Okay, so I'm definitely going to do some examples, but unfortunately that will require deleting some of this. So let me pause to see if there are any questions about these instructions, these rules. let's start by looking at,
Mark?
yeah.
So you run over all diagrams and all orientations, is that, or
No, I fix the external labeling in a cyclic order 1 through n, and I keep it fixed all throughout. Does that answer?
And
Like, I do not allow this diagram.
okay, so you fix the cyclic order, but the arrows that you put on, the
The internal arrows. Yeah, no, I don't need to sum over the 2 different ways. I just, for each diagram, I pick one and that's sufficient. Any other questions? Okay, there's some more examples in our. Oh no, there's one. I skipped one important step. Okay. Right before this last step. Okay. Eliminate all of the PE corresponding to internal edges using momentum conservation at each vertex. Okay, let's do an example. Let's start with this graph. I choose the outward orientation for my external edges. Let's call this edge 5. I pick an orientation arbitrarily. To this, I associate the following quantity. So I've got 2 trivalent vertices here. So I start there with a product of 2 vertex factors. And it's important to read these arguments in cyclic order as you go. I think I said clockwise before. I meant counterclockwise. Everything is counterclockwise in our universe. I'm sorry. So, for example, this vertex factor, reading it. Oh, that is clockwise. Yeah, clockwise. Okay, I'm good. I'm really good. That's been a long time since I did. Okay, 1, 2, 5. This one is I've got arrow 5 pointing in, so I put a minus sign here, reminding me that when I apply the formula that's now deleted, it's actually going to have the complex conjugate of epsilon 5. Okay, now a very important thing that's worth mentioning is by construction, all dependence on the epsilon E for internal edges will drop out. And the reason is the product of vertex factors is always going to be linear in each epsilon E, no matter how complicated your graph is. Let's say this is edge 7 here. Okay. The formulas for the vertex factors make it clear that the product of vertex factors is always going to be linear in epsilon 7 because it only appears once. Epsilon 7 only appears in this vertex factor, even if there are 20 other vertices in the diagram.
And epsilon 7 complex conjugate only appears as an like linearly in this vertex factor. So when you apply this differential operator, you completely remove any dependence on the epsilons of the internal edges. Does that make sense? So let's continue this calculation here. Of course, I deleted the formula now, but each of these has an overall factor of I over root 2. And I've got two factors of minus I there. So I just get a 1/2, 1 over P5 dot P5. This turns into epsilon 1 dot epsilon 2, P1 minus P2. That's epsilon 2, epsilon 1 dot P2 minus P5. Plus epsilon 1, epsilon 2 dot P5 minus P1. All of that dot with other vertex factor. Okay, so I have assigned a problem sheet that has several calculations of this order of difficulty. So that's the almost final expression for this one Feynman diagram. The only thing left is to remember this instruction that I gave at the very end. So we take this whole expression and we evaluate it at P5 equals P3 plus P4. Or alternatively, minus P1 minus P2. Those are the same thing. Because remember that we have the total momentum conservation, that these have to add up to 0. So therefore, P1 minus P2 is equal to P3 plus P4. So the instruction was to solve for the instruction was to eliminate all of the momenta corresponding to the internal edges by using momentum conservation. So if we look at this vertex, we have P5 flowing in and P3 plus P4 flowing out. That would lead us to this formula. Or we could look at this vertex where we have P1, P2, and P5 all flowing out. That would lead us to this formula. But the two are equivalent thanks to the overall momentum conservation. Okay, so this is literally the final answer for this particular Feynman diagram.
And the big dot in the middle is like a dot product dot?
Yes. Yeah, good. There are lots of dot products going on. So the thing that's inside this bracket here is a 4-component vector, because here's a dot product. So this is a scalar, this is a number multiplying a vector. Okay, so all together here, this is a 4-component vector, an element of C13. Here's a dot product times a vector. So this is also a vector. And here's a dot product times a vector. So everything inside the big brackets is a 4-component vector. And everything inside this pair of big brackets is also a 4-component vector. And the two are dotted to each other. This dot arose from that. Because to begin with, before you apply that differential operator, if I had just written this vertex factor here, there would be an epsilon 5 dot okay, now so in purple, I've now written this vertex factor before applying that differential operator. And it has epsilon 5 dot this vector, an epsilon 5 dotted here, and an epsilon 5 dotted there. And that differential operator peels this off. And now, if you're thinking there can't possibly be any connection to the amplituhedron. Yeah, you're absolutely right. Crazy. Okay, so there are a few more examples of this in the exercises, but I'm ready to move on. Are there any other questions about this? Yes.
Where do these vertex factors come from? It's the motivation for them.
Well, that would take me a little bit too far afield, but they give the definition of Yang-Mills theory. Actually, I'm going to give you a much better answer than that. Right now. Actually, am I ready? Yeah. Let me give you a much better answer than that. The answer has to do with a remarkable property we call gauge invariance. Okay. The amplitude AN constructed in this way satisfy two important properties. One, AN is separately linear in each epsilon I, and this is manifest from the vertex factors. So specifically what I mean is, if you think of this as a function of the n individual e's and epsilons, and now you rescale, you take any one and rescale it, this is going to be equal to just lambda times AN. So the whole thing will rescale by a factor of lambda. Okay, and that's manifest because for the same reason that I described, that all the vertex factors are linear in the polarizations. Property 2 is highly non-obvious. And that is that oops. This is what we call gauge invariance. Very, very roughly speaking, how could it possibly happen? Suppose you took one of these epsilons and shifted it by an arbitrary complex multiple of the corresponding p. What you'll find is that when you expand this all out and use the momentum conservation identity, you're going to end up necessarily running into things like this, terms that look like this, which were zero. Now, this is highly non-obvious, and it certainly is not true for individual diagrams. Let me emphasize that. Not true for individual diagrams. It's only true of the sum. So to get back to how this ties into your question, the vertex factors V3 and V4 are magically, I mean, we understand how, but they're basically uniquely determined by the requirement that this should be true. Are there any other questions? Okay. All right, so Now, properties 1 and 2 suggest that up to overall rescaling. You know, if we wanted to think about amplitudes projectively for a moment. AN is almost independent of the epsilon I. Now, let me explain what I mean by that intuitively. Because I don't want to give a rigorous proof here. We already said that each epsilon I has basically 2 degrees of freedom because it starts as a 4-component vector, but then it has to satisfy 2 constraints. So given these 2 constraints, each epsilon I lives in a 2-dimensional space. But this formula tells us that along one of the 2 dimensions of that 2-dimensional space, the amplitude is just independent of epsilon I. We can move along that 1-dimensional space and we don't change the amplitude at all. And if we sort of move in an orthogonal direction or move somewhere else in that 2-dimensional space, somewhere that's not along the direction of pi, the only other thing that can possibly happen is that we rescale our overall amplitude. So that's the sense in which I mean that these conditions tell us that the amplitude is almost independent of the epsilon I. And the only reason I have to use the word almost is that this is not a linear condition, it's quadratic. If all of my conditions were linear and I was counting dimensions in a linear, like if I was talking about a linear space and I added more and more linear conditions and eventually I counted that I had enough linearly independent conditions to fully specify my answer, then I would say it is indeed completely independent of the epsilon I. But because this is a quadratic equation, the precise statement is that AN is independent of epsilon I up to a choice. Let's call it a Z2 choice for each I. The basic idea is that for each, if you give me a P, there are 2 independent branches of solution. This is a quadratic equation, so there are 2 separate, disconnected branches of solutions to that equation. And you don't need to tell me the precise form, you don't need to tell me it's too much for me to ask to know every detail about the epsilon I, because the amplitude is largely independent of it. You only need to tell me, are you on this branch or on that branch? And now I can kind of give a better answer to your question, because when we think about light being polarized, for example, it can be polarized along this axis or it can be polarized along that axis. Realistically, we think more often of circular polarization, like left or right circular polarization. So there are 2 discrete choices. So in fact, there is no relevant information contained in the components of a polarization vector. The only relevant information is a binary choice of left or right polarization. Okay, so what we're going to do is we're going to trade our description of kinematic space from a collection of pi and epsilon I to a collection, to a new collection, to new variables. So I have only 5 minutes left, but I think that'll give me enough time to write these definitions and let you get started on some more of the exercises. Okay, so these are called spinor helicity variables. So first of all, you can think of a bijection between C13 and the space of 2 by 2 complex matrices in this way. And the point is, this is a useful formula because this thing has length 0 with respect to the Minkowski inner product, if and only if the determinant of this matrix is 0. So if we're looking for the momentum, if we're looking to describe the momentum of a particle, which has to have length 0, if we think about it over here as a 2 by 2 matrix with determinant 0, that means the matrix must have rank at most 1. In fact, it has rank exactly 1 because this is not allowed to be equal to 0. We don't allow E being identically 0. So E as a 2 by 2 matrix has rank exactly equal to 1. And therefore, so it's conventional to think of lambda here as a column vector with 2 components, and lambda tilde as a row vector with 2 components, so that if you take the product in this order, you get a 2 by 2 matrix with rank 1. Okay. Now, for a given P equals lambda tilde, we can solve in 2 ways. So I told you already that for a given P, there are 2 branches of solutions to this. So I'm going to write 2 representative solutions to these equations are given as follows. Epsilon plus, okay, there's a square root 2 that's a convention we'll see in a minute. Okay, I'm out of time, so I'll just describe this notation, and then we'll end. Where R and R tilde are arbitrary spinors. Oops, I didn't define that. Sorry. That's kind of important. A spinor is a non-zero element of C2. So in this case, both lambda and lambda tilde are spinors. It's just notationally we think them as being organized in different ways. We think of lambda as being organized as a column vector and lambda tilde as a row vector. But both of them we have in mind being non-zero elements of C2. And similarly, R and R tilde you should think about them as two component column or row vectors. And the last thing I haven't defined is this notation here. Defined inner products on spinors in this way. It's just the obvious way as the determinant. Okay, so these tilde guys are row vectors. So if you put two of them on top of each other, you get a 2x2 matrix. You compute the determinant, and these are column vectors. So if you put them next to each other, you get a 2x2 determinant.
Is there a vector missing from your square brackets and epsilon minus?
Sorry, but what is this I here? Yeah, this should be lambda tilde. Yeah, sorry.
I guess it's R tilde 2.
Yes. Sorry. Yes. Yes, thank you. Okay, so I have to end here, but let me just summarize. So I promised earlier that I would soon give a second definition of particle. So in spinor helicity variables, a particle, again, this is a massless spin one, is a collection of two things. It's a choice of two spinors, lambda and lambda tilde, and a choice of what we call helicity, h equals plus or minus 1. And that indicates if we choose the epsilon plus or epsilon minus branch of solutions. Okay, so just to say it for the third time in conclusion, if you fix a given p, then the solutions to epsilon dot p equals 0 and epsilon dot epsilon equals 0 come in. There are two disconnected components of solutions to that. A representative epsilon plus is a representative that lives in one of the connected components, and epsilon minus is a representative that lives in a different connected component. Choosing different values of the arbitrary spinors R and R tilde allows you to move around to different solutions inside these connected components. But up to an overall rescaling, the amplitude is independent of that choice. And that's where we're going to pick it up next time. But that's based on the two properties that I had written on the board, the scaling property and the gauge invariance. Okay, so this is the definition of a particle in spinor helicity variables. And that's all for the first lecture.